Good morning, everybody. I was asked yesterday, why did I appear before Christmas in this red robe? This is an old joke. Do you know the Monty Python sketch about the Spanish Inquisition? These are the costumes from there. A long while ago, while I gave this lecture, several years ago, three of the students of my group appeared here and played in the middle of the lecture, the Monty Python sketch about the Spanish Inquisition. And I met one of these guys again the day before the last lecture before Christmas. And we talked about this and that, and among other things about this. And then he asked me to wear this. Yeah, and so I did. Nobody expects the Spanish Inquisition. Okay, where are we? Stellar dynamics. We arrived last time at the Jeans equation. Let me write this down again. We're going to need it anyway. So, we had a continuity equation. And we had a replacement for the Euler equation. Where sigma square is the velocity dispersion tensor. So it's a tensor of containing all components of the velocity dispersion. V1 times V1 square averaged, V1 times V2 square, no, V1 times V2 averaged, and so on and so forth. Okay, and we argued already last time that these equations, of course, have a strict resemblance to the hydrodynamical equations, simply because both of them are conservation equations. So you recognize here, for example, in the Jeans equation, the total time derivative of the velocity, the acceleration on the right-hand side. And you see that this equation simply says acceleration is given by a replacement for the pressure. That's the kinetic origin of the pressure here, and the gravitational force. And we have a continuity equation for the stars, for example, in a stellar system, or for the galaxies in a galaxy cluster. But notice also the differences to hydrodynamics that I pointed out last time. I said last time that these conservation equations hold in hydrodynamics because we have so intense interactions between the individual particles that once we integrate the inevitable collision terms over velocity space, the right-hand side of our conservation equations disappear after taking velocity space moments. Here we have assumed collision-less conditions from the start. And so here we have assumed that collisions are absent. In hydrodynamics, we have assumed that collisions are extremely frequent. They lead to the same set of equations, but this, of course, has limited applicability. I showed you two examples last time. One was an example where the relaxation time in the stellar system is very, very long. In other words, collisions are very, very rare. This was the example of a galaxy, of the stars in a galaxy. And then this is a good set of equations. And I also showed you a counterexample, namely the stars in a globular cluster, where you have approximately 10 to the 5 stars, within, let's say, 10 parsecs or so. And then collisions are so frequent that this is not a good equation anymore. And if there will be some time left towards the end of the lecture, I'm not sure about this yet, we can speak about replacements. Because if you encounter situations like that where relaxation time is very short, or comparably short, after all, it still was 10 to the 8 years, then we need some way to take the collisions into account. And then the next step you can go is the so-called Fokker-Planck equation, the Fokker-Planck approach. And maybe we get to that, or maybe not, I'm not sure yet. Anyway, that's the Jeans equation. Now, we said last time that we will need for the interpretation of many systems in astrophysics a radial version of the Jeans equation. And this started a lengthy calculation in which we had to transform the Jeans equation, or rather the Liouville equation, into spherical polar coordinates. And I would like to re-enter into that calculation, not doing all of that again, but just writing down where we were. And we had arrived at an expression for the time derivatives of the velocity components in spherical polar coordinates. And this is what we need in order to express the Liouville equation appropriately. So this was dr phi, okay. But now velocity components, or squared velocity components. Then we had this one. I hope it's correct. Okay, that should have been the last thing that we arrived at last time. Okay, this looks horrible, but okay, we have to go through that, and then we will have to simplify that. Okay, now what do we need this for? We need this because we need to express the Liouville equation in these spherical polar coordinates. So we start with the same equation, of course. The physics is not changed. But this is changed. So we have the easy part, and now the awful part. There's a global minus sign here. I have to adopt this there. And now we have VR dot. So terms like this, right? And so on and so forth. Now I'm just copying these expressions here and multiply with the appropriate derivatives of the phase-space distribution function. Must be funny to watch, isn't it? We are done soon. No more, no less. Who wants to deal with that equation? Nobody, of course. So what are we going to do with it? It starts over here, right? So now we are going to integrate this over velocity space and multiply at the same time with radial velocity component. Aha. Okay. So we apply this operation to this monstrum here. And then we are going to use relations like that again. Okay, that's the definition of the velocity space average with a phase-space density. And we will make frequent use of partial integrations afterwards, but we'll see about that. Okay, so I need to start here. If I apply this operation to that expression here, I get dtn average over VR. Okay? I can exchange the time derivative and the velocity space integral. If I carry out the velocity space integral, I get this after taking this radial moment, and I have this expression here. Okay. Same thing there. Except that now I'm getting a VR squared average times n, radial derivative. Aha. It doesn't look so horrible, does it? Now, and now I'm running out of sync. This is this term here. And we go on. Now I'm here. Okay. Now we have taken care of these terms here. And now I need an interlude. And for this interlude, I'm going to take this term only and show the calculation that follows at one example, and then move with higher speed through the other terms. So let's focus on this term here, and let's see what happens. So we have d3v vr dr phi minus v theta square plus v phi square divided by r dvr f. Well, that cries out loud for a partial integration. I'm now going to take a partial integration by taking this velocity space derivative and applying it here. Okay? Okay, then this turns, well, first of all, I get a global minus sign. Then this turns into a 1, this turns into a f. And then you see, this is just So this is n times dr phi from this term here. And then minus n over r v theta square averaged plus v phi square averaged. Okay, that's what happens to this term here. Okay, but then we will also have terms in which we cannot use this trick of partial integrations. Right? Because there is, for example, if I take this term here as an if I take only this potential gradient here, and I see what happens now. You see what happens now is that I can carry out the v theta integral here, which gives me a boundary term in f at the limits of the v theta integration. So at v theta between minus and plus infinity here. But at these positions, or at these velocities, the phase space density will be 0. Okay, so for these terms, where I cannot do this partial integration, the terms will drop out anyway. So what does this mean? This means that this term and this term will go away. This will integrate to 0, such as this one, but not these two, right? Because they contain a v phi. Not this one, because that contains a v theta. Aha, okay. But in any case, through the boundary terms here that occur in this and that term, these terms will go away, and we have gotten rid of 3 of these terms. How nice. Good. We already know what that is. I'm copying the result from above. Oh, wait a moment. I said it but didn't write it down. There's a global minus sign because of the partial integration. But I have to subtract this. Okay, so I have plus n dr phi. Okay, minus n over r v theta square plus v phi square averaged. Okay, now I'm here. I don't have to take care of that one. Now I do have to take care of that one. I have to multiply with VR, gives me a VR squared. I can play the partial integration trick on that v theta here. Then this v theta is gone and I have an f. The integral over the f gives me a spatial number density n. And the partial integration changes this minus sign to a plus sign. So this gives me plus n average VR square over r. Now I'm here. Right? This turns into that one. This one is gone. Goodbye. This one is gone. Here I have to do partial integration again, because here I have a v phi, which is the same as the variable with respect to which I'm taking the derivative. So the partial integration changes the sign. I multiply with VR. I'm taking the average, and gives me another nvr square average divided by r. Now I'm here, or I have been here. Now the final thing that's left is this one, and this gives me plus n average VR with theta divided by r cotangent of theta. Okay. Beautiful is different. But now, look, what we are going to do now is the following thing. We say that radial and tangential velocity components are uncorrelated. This means that we assume isotropy in the velocity distribution. Okay? Now, isotropy is a difficult term here. I'm first of all assuming only that the tangential velocity components, either in theta or in phi direction, are uncorrelated with the radial velocity components. If that is the case, and of course this is always the case, these are gone. Okay? I'm further assuming that I'm in a stationary situation. I have a stationary object in front of myself. So this one also falls victim to that. Okay. So in order to make this more explicit, these are the reasons for red and yellow. I'm going to do one more thing, okay? I'm going to assume that these two are equal, in line with the symmetry assumption. Right? I'm assuming that the radial and the tangential velocities are uncorrelated, and I'm assuming that the two components of the tangential velocity have the same dispersion. And I'm going to introduce new symbols. I'm calling these dispersion sigmas. And I'm going to assume that sigma theta square, which by assumption of isotropy is equal to sigma phi square, is a certain fraction of the radial velocity dispersion. So I'm introducing a new function beta, which if one says that sigma theta square and sigma phi square are both 0. So if beta is 1, then I have radial motions only. If beta is 0, then the tangential velocity dispersions are the same as the radial velocity dispersion. And therefore beta is called the anisotropy parameter. It's not a parameter, it's a function, but okay. So this is called the anisotropy parameter. This agrees with our general assumption of isotropy in velocity space. And again, right, I point out that isotropy is not supposed to mean that all velocity dispersions are the same, but that the tangential velocity dispersions are the same. So we still have an anisotropy left, which relates the tangential velocity dispersions to the radial velocity dispersion. So in other words, if I pick out a certain point in my overall mass distribution, I would have a velocity ellipsoid. Okay? This has a radial dispersion like that, and it has a tangential dispersion like that. And this assumption, with theta square or sigma theta square and equals sigma phi square, just means that I can rotate this velocity ellipsoid about its long axis. And the beta quantifies by how much the axes of these ellipsoid are different. Okay? So I'm defining a velocity ellipsoid here. It's a rotational ellipsoid. Its axis ratio is set by beta. If beta is 0, it's a velocity sphere. If beta is 1, the ellipsoid shrinks to a line. All right, so under these assumptions, I can write 0 equals dr n sigma r square. Next one is lost, next one is lost, next one comes later, next one comes also later. Next one is this, right? This is 2n over r sigma r squared. So now I've taken into account this one, these two. Now I'm taking these. And then there's only one term left, equals 0 I already have. Okay, now that looks much more manageable, but we are not done yet, all right, because these two are the same, and they are a fraction of sigma r. And if I take this sigma r squared, and if I take this definition of the anisotropy parameter into account, this leads to this equation, which of course is much more manageable than before, and of course allows much less freedom. But we have reduced it now to something that we can deal with. And this is often called the radial Jeans equation. Okay, lovely. You can solve that. You can solve that immediately. You can give a closed expression for the solution. Look, it's very simple. The unknown function is just the n sigma r squared. What is this? This is an ordinary ordinary first order differential equation, which is inhomogeneous. Now, how do you solve that? First of all, you need the general solution of the homogeneous solution. Well, that's very easy. Look, if I take away the inhomogeneity, the right-hand side is just 0, and then you see that the radial change of our searched function n sigma r squared is proportional to itself. The solution must be exponential. So you see, the homogeneous solution is given by this expression here. So I can write it in this way. So this means that the ln of our searched function n sigma r squared is an integral over beta of x, an isotropy parameter can vary with radius, beta of x divided by x, up to r from somewhere. It doesn't matter. Let's take 0. Plus an integration constant which I call ln c. And of course, if I change the lower limit of that integral, then ln c will change, but this doesn't matter. Okay, so in other words, the homogeneous solution looks like n sigma r squared equals some constant c, some amplitude, times the exponential of minus 2 and then this integral here. Okay, fine. Now suppose beta is a constant. Could be, right? Could be 0, then just 1. Suppose beta is a constant, then you get here the logarithm times 2 times this constant. So this will turn into a power law of r if you exponentiate it, and so on. Okay. Now, how do we solve the inhomogeneous solution? We vary the constant, right? Like PTP1, mechanics 1. Right? Okay. So in order to solve the that's the homogeneous solution. It's the general homogeneous solution, right? Because the constant c is free. Okay. And since it's a first order differential equation, one of them is enough. Good. Now, let's vary the constant. So in order to get at the inhomogeneous solution, I am elevating the constant c to a function. Then you see the derivative under these conditions is what we wanted to have, namely 2 beta over r times n sigma r squared. This is if I apply the radial derivative to that term here. And that, of course, solves the homogeneous equation. Well, this is how we made it. But now we get a c prime. That's the derivative of c of r with respect to r. Now times this integral. Okay, and this is supposed to be, according to the radial Jeans equation, 2 beta over r n sigma r squared. Well, this is taken care of. Minus n dr phi. This is what we still need. So you see, c prime has to satisfy exponential of plus 2 integral from 0 to r times this one here. Right? And again, you can directly integrate that. So c of r. Now what do we do? Minus integral from somewhere to r. Still need to fix somewhere. Of this, n dr phi exponential of 2 times this. Now I need another integration variable. I call this y. And now I'm fixing the lower integral boundary such that c becomes 0 at infinity. It seems to be a good choice, right? That the amplitude of this radial pressure term here, n sigma r squared, vanishes at infinity, and therefore I'm going to integrate from infinity to r, outward in. Aha. Well, then let's integrate inward out and change the sign here. Okay, fine. Now we know what C of r is. Now we just need to combine these two. Since this is an integral over y, and this is contains an integral over x, I can pull this complete expression into that one. And I can combine these two exponential terms. Sorry, this needs to be y now because y is the integration variable. Now you see, from an integral from 0 to y, I'm then subtracting an integral from 0 to r. So that's going to turn into an integral from r to y. Okay? I need more space. Yeah. Okay. So to repeat, this is now our varied, this is now an empty laser pointer. I always wondered what this is for. This is now our varied integration constant. Right, that takes care of the inhomogeneity of our differential equation. I need to multiply these two now in order to get n sigma r squared, the radial pressure component. Okay, now I can simply pull this exponential term under this integral here. Right, because in terms of y, this is a constant. I can pull it under the integral. Then I have integral 0 to y minus integral 0 to r, so that's an integral r to y. In other words, n sigma r squared is an integral over dy that now goes from r to infinity. Now let me write the arguments explicitly. Right? N must be taken as a function of y. Then we have the radial gradient of the potential taken at variable y. Right, that's our integration variable here. And then I have an exponential of 2 times integral r to y beta of x divided by x integrated over dx. That's our solution. Suppose you have to do with a spherically symmetric mass distribution, which is pretty much in line of our assumption anyway, then you know that the gravitational potential is given by gm of y divided by y. Negative. So if I take the radial gradient, and evaluate it at evaluated at radial coordinate y, I'm just getting this expression here. So similarly, what you often see for the solution of the radial Jeans equation is this expression here. Okay. What does this tell you? Remember, we are on the way of relating. It's interesting. We are on the way of relating observable quantities to the mass distribution. And we observe an object. We want to know what, parentheses, the hell, is the mass distribution like? For example, we want to infer from spectroscopy what mass distribution is underlying the motion that gives rise to the spectroscopy that I see. We are not there yet, but we have made a big step forward. The big step forward is the following. This is the radial velocity dispersion. This, of course, has to do with the velocity dispersions we are going to see. We have to put more work into that. But this comes close to to an observable quantity. Not quite yet, but okay. So this tells you if you observe velocities like that, they are related to the mass distribution like that. And of course, you don't know any of the ingredients that go into the right-hand side. You just have observations that indicate the left-hand side. So what do? You assume a mass distribution. You assume an anisotropy parameter. And then you see whether that fits to the observations. Aha. Well, what else can you do, right? So let me show you an intermediate step with an assumed mass distribution. So this is an extension of the notebook. Here I am assuming a mass distribution, which is called the Hörnquist mass profile. Hey. Okay. Rho of x, you see that, right? Rho of x is 1 over x times 1 plus x to the third power. That's the Hörnquist profile. I didn't care for making this a dimensional expression. And of course, you would have to multiply this with an amplitude, rho 0, and you would have to set x equal to the physical radius divided by some scale radius. Doesn't matter, right? Okay, so that's the Hörnquist profile. And then I'm assuming an anisotropy parameter, beta of x, that goes like a plus b times x. If a and b is 0, well, then I have isotropy, otherwise not. And then, of course, by its definition, beta should not be more than 1, right? Because velocity dispersions have to be positive semi-definite. So therefore, beta is limited to from 0 to 1. Okay, then you see some functions defined. Now, of course, well, the function density here, that just repeats the Hörnquist profile. I was thinking, well, maybe you want to try a different density profile. Then it doesn't make sense to give the analytic solution of the density, which of course you could give, right? So therefore, I'm integrating the mass also numerically. That's not necessary, but if you change the density profile, you might have to do this numerically. Okay, and so on and so forth. And then you can calculate the radial pressure here for different assumptions for the anisotropy parameter. So the first one, the blue line, is for isotropic velocity distribution. And all I wanted to show you with this is, even if you have a single mass distribution, the velocities that you see will differ very strongly in the core. They differ by a factor of 10 in the core. Right? If you change the assumption on anisotropy, and of course you have no idea about the anisotropy. And then in the respective papers, you see this one little sentence somewhere in a footnote or so, saying we assume isotropic mass distribution or so. Then you arrive at conclusions, and you say this galaxy has a mass distribution like that. And you say, given that anisotropy assumption, the mass distribution is like that. Okay. All right. So this has several purposes here. First of all, I wanted to give you a numerical code that you can play with. Second is, this is a warning, right? If you read the respective literature, watch out for the anisotropy that has been assumed. It changes the results, or may change the results dramatically. And of course, I've normalized this here such that at large radii, the velocities are the same. They don't need to be, right? You could fix them somewhere at some radius, and then of course the discrepancies would be somewhere else. Okay. Now, time for the break, but I have a request. The request is the following. If you now look at the web page of the lecture, you see here, link to the lecture evaluation. Please go there and fill it in. Please do so now. Because experience shows that if we don't do this during the lecture, then nobody does it. Except for those who want to complain. That's of course you're right. But it skews the distribution a bit. And of course, the whole evaluation system is such that every one of you can evaluate the lecture multiple times, including me. So if you give n negative evaluations, I will take care of giving 10 n positive evaluations. No, of course not. Please do that. And I suggest you do it now. So while I'm cleaning the board and walking around and so on, you can do that. Do you need more time? Are you done? No. Fine. Thank you very much. Now, let's move on. Let's relate this now, this result that we had about the radial pressure here, to observable quantities. So suppose we have a spherical object here somewhere, and we observe it along a certain line of sight. So I'm thinking of a galaxy somewhere, and our line of sight pierces through it at some separation, let's call it S, from the projected center. Okay? Now I'm going to use the following coordinates. There's the S here, there's of course the radius. There's of course the radius. within the galaxy, the radial coordinate that we had before. And now I'm going to use the coordinate z along the line of sight such that z equals 0 is at the point of closest approach. Now, I need a projected surface density. In other words, I need a quantity like this. And I need to integrate the number density or the mass density along the line of sight, and I call this the projected density I of S. Projected density, or the surface density as it is often called. Okay, now how do I find this? Let me first use z squared plus s squared equals r squared, the Pythagoras here, z squared plus s squared equals r squared. Keep s fixed and use this to see that 2z dz equals 2r dr. Okay. So therefore, I can replace the dz by r dr divided by z, or r dr divided by square root r squared minus s squared. So that's what we need for the projection. That's often also an expression that you very often see. But this transformation is, of course, not monotonic. Right? It has two branches, one from 0 to infinity, the other one from minus infinity to 0. So I need to split up this integral here. And write I of s is 2 times integral from a lower bound. Now, what is the lower bound? The lower bound for integrating over r is the smallest radius that I can get to, and this is s and not 0 anymore. So that goes from s to infinity 2 times. Now r dr divided by square root r squared minus s squared. And now I can insert here n of r. Okay, that's the projected surface mass density. Okay, this is one thing I need. The other thing I need is I need to relate this velocity ellipsoid that we had before to an observable velocity. So for that, I'm going to use the same sketch as before. Here's our line of sight, there's the center. Now I'm here, and there's our velocity ellipsoid. And I'm assuming that there is this angle alpha over here. Now, the small axis of this velocity ellipsoid is sigma theta, or equivalently sigma phi by our assumptions of isotropy, of tangential isotropy. And the long axis is sigma r. So the velocity, the parallel velocity, parallel to the line of sight, that I'm going to see is cosine alpha sigma r plus sine alpha sigma theta. Strictly speaking, this is massively incorrect, because we have a statistical quantity on the right-hand side, namely the velocity dispersion, and we have a velocity on the other side. So what I should more carefully write is, if an object has a radial velocity of Vr and a tangential velocity of V theta, then the velocity that I see would be this expression here. But I'm going to square it anyway. So if I take the average squared, the squared average here, no, the average squared, yes. That's going to be sigma r squared cosine square alpha plus sine square alpha sigma theta square. Now, let me correct that here, plus sine alpha, cosine alpha, average over VR with theta, which is 0 by our assumption. So the last term is 0 by our assumption. So we have sigma r square cosine square alpha plus, now sigma theta was assumed to be sigma r squared times 1 minus beta, okay, times sine squared alpha. So you see here I'm adding the cosine, the sine in squares, so this gives the sigma r squared, and now I have 1 minus beta sine square alpha. It's correct, isn't it? Okay, now I can relate the sine of this angle alpha to quantities that I already have, because the sine of alpha is s divided by the radius. So I can write this as sigma r square 1 minus beta times s squared divided by r squared. R I have to integrate over, s is fixed by my observation. All right. Now this would be the radial velocity, sorry, this would be the line of sight velocity dispersion of a single star. But of course there is not a single star. So I have to weight this expression here with the number density of stars. But then of course I also have to normalize by the number density of stars. So in other words, I'm now going to calculate a line of sight velocity dispersion. And this is now the first quantity that we can really see. This I can measure with a spectrograph. Now what is this? This is the projection of n of r times this result here, sigma r square 1 minus beta s squared over r squared. And look, there's the n sigma r squared. And we know how to relate n sigma r squared to the mass distribution. Okay, now we have to project again. And I'm doing this as before with this projection element here, r dr divided by square root r squared minus s squared. But then I have to integrate from s to infinity, and I have to double that, like before. And I need to normalize this by the projected density alone, so by the surface density. You can think about this in the following way. So n times the projection element divided by I of s. This is a probability for finding a star at projected radius s from the center of the galaxy. And with this probability, I'm weighting the velocity squared here, and I get the observed velocity dispersion. All right. Now you see, strictly speaking, we have everything together that we need. Suppose you measure a light distribution in the galaxy. You might infer what the surface density distribution is. But of course, even there, assumptions enter. Right? Because you observe a light distribution, so that's a distribution of surface brightness, for example. And you know that this is caused by stars, for example, if you target a galaxy. But then you don't know whether the stars are equally distributed in color, for example, or brightness, across the galaxy. But if you can assume that the stellar population, for example, doesn't change across the galaxy, dangerous assumption again, but then you might know what I of S is. If you turn this around and you say, okay, I guess a mass distribution, or I guess a number density distribution of the stars, then of course you know what that is. Then you also know what that is, provided you also guess an isotropy parameter. So then you can't invert this equation, but you can make a forward prediction of the observed velocity dispersion. And then you can see whether that matches the observation. And if it doesn't, then you have to change this. And then, for example, you can stick with the radial mass distribution that you have already assumed and vary the anisotropy parameter and see whether by changing the anisotropy you can make a certain mass profile fit to the observations, or whether you will have to change the mass distribution itself. Okay. This is one central result that we were driving at. Right? This tells you how to relate the width of a spectral line to a mass distribution here. And you see how convolved that is. So n sigma r, you see, contains an integral over an integral, and integrals smooth out fluctuations, right? Smooth out variations. So integrals remove information. So what you see here is multiply convolved, right, with a mass distribution that you want to know. Okay, but that's how it is. I mean, the alternative would be to fly there, which takes a lot of time. It's very tedious, right? So what can you do? Okay, let's have a brief look at the anisotropy parameter again. Remember, we had an equation like that. dr n sigma r square plus 2 beta over r n sigma r square equals minus n dr phi. All right, so now you can solve this for beta of r. What do you need? You would need minus r divided by 2 n sigma r squared a n dr phi plus dr n sigma r squared. All right, so you can use that relation if you have any other information in order to guess what the anisotropy parameter could be. But of course, you see, all right, there's the radial derivative of a quantity entering that you don't really know either. Nonetheless, this relation here, which comes from the radial Jeans equation, allows you to substitute for the beta in this expression here. And then this equation here turns into a single equation relating the radial pressure component here, the n sigma r square, to the observed velocity dispersion here. So you find this in either way, right? Either with an explicit beta parameter inserted here, or you see it in the way where the beta parameter has been replaced by this expression here. So you see a more complicated version, you see this version here. It just depends on whether the radial Jeans equation has been used in order to insert this. Okay, now let me show you examples again. Again, for the fun of it. So again, I'm starting with a Hörnquist profile. To recall that, Hörnquist profile looks like that, 1 over x times 1 plus x to the third power. Then this is its protracted density. And of course, since you protract, it usually goes with a power of radius shallower than the three-dimensional profile does. And now, this is the line of sight velocity dispersion. And in order to highlight the differences between different anisotropy assumptions, this is without this normalization here. Okay, if you take this normalization into account, you see much flatter curves, but the line of sight velocity dispersion looks like this here. And again, you see that what you can observe, right, can largely deviate or can largely vary with different anisotropy assumptions. Okay. If you run this here, you will see that it takes a lot of time. This is because you integrate over an integral of an integral. Okay, good. Sometimes you have to. So I didn't run this on the fly here and prepared it so they can have a look at it. But try it out, right? I mean, you can lower this number 64 here to maybe 8, right? And then you can play with that. All right, so far so good. This is what I wanted to tell you about the radial Jeans equation. So first of all, about the Jeans equations themselves. Then about the radial version of it, and about the relation of underlying mass distributions to observable quantities. All right. And again, if you read statements in the literature like the mass distribution is like that, do search for the assumptions that enter into this statement. Of course, there is no problem with making assumptions. We can't do otherwise, specifically in astrophysics. But make them explicit, please. Okay. Now, since you know the Monty Python sketch from about the Spanish Inquisition, you probably also know what it means to say, and now for something completely different. And now for something completely different. Let us return for a moment to the virial theorem again. And for that, I'm going to start with an intermediate step in our derivation of the Jeans equation. Which looked like that. How did we get there? We took the Liouville equation. So again, we start with a collision-less system. We start with the Liouville equation, and we take the first velocity moment. And so we multiply it with the velocity and integrate over velocity space, and then this is what we are getting. Okay, and now I'm going to do the following operation. I take an integral over d3x. After multiplying the whole expression with the mass of a single star, assuming that all of them are the same, and tensorially multiplying with the position vector x. That's the operation I'm going to apply. Okay, then what do we see? Sorry. number density is now changed to the mass density because we have multiplied with the mass of a single object, and now we have this tensorial expression here. All right. Next step is this one. And the next step is this one. Okay? Now you may recognize some of the terms that we spoke about when the Spanish Inquisition was here just before Christmas. Namely, this expression here is the negative tensor of potential energy. Remember, we discussed this when we spoke about the virial theorem just before Christmas. So that's potential energy here. And so that is Chandrasekhar's version of the potential energy tensor, and its trace is minus a half the volume integral of rho times phi. Now that makes a lot of sense, right? You take the density rho, you put it into the gravitational potential phi, you get a potential energy density, you integrate this over space, you get a potential energy. If you take a factor of minus a half, of minus 1 into account, and if you take a half, because in that way, if you decompose the mass distribution into individual objects, you would count all of them twice. Okay. So that's that. Now, let's take care of this one here. And remember the trick that we applied before Christmas multiple times? We try to identify volume integrals over divergences in the first place, and then subtract the correction terms. So this I would like to write as this one here. But then, of course, I'm doing things wrong. Right? This is nice because now we have a volume integral over a divergence, which by Gauss' theorem would give us 0. But now, of course, I have to subtract what happens if I apply the gradient to the remaining factor. But this is nice to remember. This is a tensor consisting of elements di xj. That's the unit matrix. Lovely. This one goes away. And this one you see is just the integral over rho times v squared times the unit matrix. That's 2 times the kinetic energy tensor. Aha. And this one, maybe you recall that as well. That's 2 times the double time derivative of the inertial tensor of the stellar distribution here. How did we go about this? So we defined an inertial tensor like that. And it takes care of the mass distribution in the object, and said that the total time derivative is the partial time derivative of rho, because that's the only thing that changes over time. And the rest are just fixed spatial coordinates that we integrate over. Then we replace this by the continuity equation by minus divergence of rho v. And wrote this is minus d3x. Now let me write a this one here. Now we play the same trick, right? We pull the divergence out front of the integrand. And then again and again, right? So this would be 0. Now we would apply the divergence to both of these terms. Both of them give us a unit matrix. And then we have to take another time derivative, which we apply to this one here. That gives us this term. And the application of the gradient operator to both of these factors give us a factor of 2 that we have to divide out again. So this is why we have 1/2 d2i dt square here. All right, so summarizing, we can write the virial theorem in stellar dynamics as this one here. Okay. In a stationary situation, you see that this recovers the virial theorem as you know it, right? That the tensor of kinetic energy is minus 1/2 times the tensor of potential energy. And now, of course, you can take the trace and you recover the original version of the virial theorem here. Now, this tensor K of the kinetic energy is worth a further consideration. Right? We have this expression here. And now, remember, we already made this velocity split, right, into split into the mean velocity plus a perturbation or a fluctuation about it. So I can split it in this way. And now, by definition, the average of the fluctuations is 0. And this means that I can split up the kinetic energy term, or the kinetic energy tensor, into 2 parts. Where this v now is the average of the velocity, plus a term that we can write in our previous notation as rho times sigma squared. That's the velocity dispersion tensor. Now, this is sometimes called T. That's the tensor of the macroscopic velocities in the stellar system. And this is since sigma squared is a velocity dispersion tensor, right? It's this object here. This is a tensor that replaces the volume integral over the pressure that we had in the virial theorem in hydrodynamics. Okay, so this corresponds to a pressure term and is often written as a capital pi. Okay, so you recover the individual terms again that we had in hydrodynamics and see again that the pressure in stellar dynamics is replaced here by a velocity dispersion tensor, which of course, unlike the pressure in hydrodynamics, can be anisotropic. Right, so you can have an anisotropic pressure here, which you usually do not have in hydrodynamics, but of course which you may have in magnetohydrodynamics. All right, so sometimes you see this expression here quoted as the virial theorem, which, as you see, is not quite complete, but is okay for a stationary situation. And sometimes you see the kinetic energy tensor split up into contributions T and pi. All right, and because the virial theorem is so often quoted in astrophysics, right? If you want to have average relations between kinetic and potential energy, you need to know about this. And it is so important, of course, because everything that you see in astrophysics needs to be related to some kind of dynamical quantity if you want to know about mass distributions, for example. And this is perhaps the most simple way to relate velocity information that you may observe in the width of spectral lines to information about potential depth, right, to mass. All right, so that's a very important statement. That is what I wanted to conclude with today. Now let me very, very briefly go through the quiz questions again. Yes. Yeah, if you think about the definition of the kinetic energy, that would be mass divided by 2 times v squared. All right, so that explains the factor of 2. So that if you take the trace of this thing, right, you see rho over 2 times v squared. Right, so the factor of 2 is just to align this with the usual definition of kinetic energy. Oh, indeed. Thank you. All right. All right, let me briefly go through the quiz of last time and the answers that I thought were correct. So, number 1, thermal plasmas are characterized by several scales. Well, there's no doubt about that. Largely determining their properties. Which of the following statements are correct? Number one, the Debye wavelength is the typical wavelength of sound waves in a plasma. Well, this is nonsense. Number two, the plasma frequency determines how quickly plasma electrons can respond to electromagnetic perturbations. We saw that when we looked at the electromagnetic dispersion tensor. Right? Because if you go with the incoming electromagnetic radiation below the plasma frequency, then the electromagnetic radiation just cannot propagate anymore. Point charges are shielded in the plasma on the scale of the Debye wavelength. That's how we derived it. Number four, the Coulomb potential of point charges is changed to Yukawa form with the Debye scale in the thermal plasma. That's almost the same statement. Number five, a plasma is called ideal if the Debye length is very small. No. An ideal plasma has a large number of electrons within a Debye volume. Okay, number two. The dielectric response function is essential for studying the propagation of electromagnetic waves in thermal plasmas. With which of the following statements can you agree? The dielectric response function, number one, can be decomposed in a longitudinal and transverse part. We almost made a hobby out of that. Right? Number two, the dielectric response function is derived from the linearized Liouville equation. That's important. Otherwise, we would have no clue what to do. Has poles and therefore an imaginary part. That's what we explicitly showed. Number four, describes linear and nonlinear response alike. No. Is derived exclusively from Maxwell's equation. No. What other equation did we need? A Liouville's equation. And finally, is a scalar function? No. Okay, number three. In magnetohydrodynamics, a frequently used concept is that of a cold collisionless plasma. What does this entail? In a collisionless plasma, particles interact through a collective potential. Right? They do not interact through collisions, individual particle collisions, but they move in a joint potential. Okay. That's what's meant by collisionless. This does not mean that they do not interact, right? Be careful about this. Number two, a plasma is called collisionless if its particles do not interact. Wrong. They do interact through their joint potential. Number three, a plasma is called cold if the thermal energy of its particle is negligible. Does not mean the temperature is zero, right? Because otherwise you would have difficulties maintaining a plasma. Okay, number four, in a collisionless plasma, only collisions between ions are neglected. Okay, number, how many? 5. The temperature of a cold plasma is strictly zero. No. Number last, a plasma is called cold if its positive charges are at rest. Well, almost, but that's not part of the definition. Okay, number 4. Faraday rotation is an important effect for detecting and quantifying magnetic fields in astrophysical plasmas. Which of the following statements can you endorse? Faraday rotation occurs in non-magnetic plasmas at sufficiently high temperatures. I just put this in for the fun of it. This is complete nonsense. Requires electromagnetic waves below the plasma frequency? No. Because below the plasma frequency they wouldn't propagate at all. Is due to vorticity in the plasma flow? No. Number 4, can be detected because it depends on the squared wavelength of the electromagnetic waves. Remember, otherwise you would have no chance, right? You have to observe the linear polarization orientation at different wavelengths in order to infer what the degree of Faraday rotation may be. Number, 5, responds to the magnetic field component aligned with the line of sight. That's correct. And this is because of its origin, right? That you can rotate electrons or gyrate electrons more easily with than against the magnetic field. Okay, number 6, originates from birefringence between electromagnetic waves with different circular polarization. That's the origin. And the last one is wrong, originates from birefringence between electromagnetic waves with different linear polarization. No. And we identified circular polarization modes. And 2 different branches of the dispersion relation for these 2 circularly polarized modes. Number 5, hydromagnetic waves are perturbations of the density, velocity, and magnetic field in a magnetized plasma. How would you characterize them? Now, hydromagnetic waves, can only be longitudinal like ordinary sound waves. No. Can be decomposed into fast, slow, and alphane modes. Yes. Are always accompanied by density perturbations. No. Remember our discussion of the alphane waves, right? They are not accompanied with density fluctuations. Can only be driven by combinations of magnetic and thermal pressure, in parentheses, alphane waves. No, because alphane waves are only driven by magnetic pressure fluctuations. As the next answer says, can have zero phase velocity. Oh yes, right? We saw examples of that, both for the alphane modes and for the slow hydromagnetic waves. All right, that would have been it. I don't know, can you see these correct answers? If you log in, I can see them because I made the quiz, right? Okay, I did not forget that you asked for opening the other quizzes again. I just didn't do this yet. All right, that was the menu for today. I hope it tasted well. Next course to be served next Monday. Yes? I need to switch it free again. Yeah, they have a limited period of appearance, and I need to extend this. I know you asked for it, I didn't forget that, I just didn't do it yet. Yeah, I was wondering whether you can see them. You can't. That's good. But nonetheless, you should be able to see that afterwards. Okay, good. I'm going to check this out. All right. See you next Monday.
Versucht, aber gescheitert. Nice. Die willst du sicherlich vorstellen. Ich meinte erstmal